Hello, my name is Brugard, the CEO of Wolfram Mathcore, developers of SystemModeler. In this presentation, I will show how you can use Arduinos together with SystemModeler to create experiments in your labs.
Okay, thank you, Phil. As Phil said, hardware in the loop simulation is my first presentation ever when I'm using any hardware except my computer. So I guess I will see if I'm the first one to get something to work the first time I run some hardware. Anyways, this presentation I worked together with Leonardo Laguna Ruiz, one of our developers in Linköping. He likes Arduino, Raspberry Pis, and similar stuff quite a lot. So he does a little bit of experiments at home. And at the end, I will be displaying one of his creations, which is this ball beam here. But before I do that, I will start with an overview of connectivity in SystemModeler. And then I'll give the Arduino example, including this one and a couple or more, before I wrap up with a very short coming soon section. For the things I will mention here on connectivity, some of them I will just briefly mention, some I will show an example of. But the focus will be on Arduino. So first of all, if you have a SystemModeler model, you can always export it. And there's two main ways to export it. You can either export it as a simulation executable. So when you have your model, every time you simulate it, it creates a C code, and that C code, or C++ actually, is then compiled. That executable you can use in any way you like, without any license conditions from our side. If you're using any library that has specific license conditions to it, then of course you have to apply to those. And I actually saw one example of that today at the additive booth where Smart CAE was developing a simulator using the executable behind the scenes. But you can also use the FMUs, which is a standardized interface functional mockup unit, that makes it possible to export to a lot of different tools. So we can look at that list here for some examples, meaning that if you have a model in SystemModeler and want to use it in, for instance, ANSYS Implorer, or in Car Maker, or in General Energy Systems, NI Veristand, and so on, you can just click FMI Export. It will export your so-called FMU, which you can then import in that tool and use it as part of their system. So to make this a little bit easier to understand, I'll show an example from NI Veristand. So basically, here is an illustration of the setup. We have a model of some tank system that is developed in SystemModeler. And for those of you that have run the introductory examples in SystemModeler, probably run that model because it's just a system of 3 tanks where the levels of the tanks are governed by some controller. Once that has been developed, it is deployed or exported to the FMU. And with the FMU, we import that to NI Veristand. And NI Veristand is from National Instruments, and the purpose of that is to test for real time performance. So basically, by getting into NI Veristand, you can test it, how it will perform together with different hardware, and then deploy it to hardware. So basically, I don't have NI Veristand on my computer, so I cannot run it live, but I can at least show you kind of the type of result you can get from that. And this is the NI Veristand user interface, where you can build up systems like this with knobs and plots. And the interesting thing here is not the interface itself, but that it's actually testing things for real-time real-time performance. So you will get a report telling you whether it would work for your application or not, whether you need to improve performance of your model. Based on that, you can take the result back to SystemModeler and develop the model further if you need. Or perhaps you see that you have a lot of margin, you can do a more advanced model, more detailed model, and then you do that, and you can go back to NI Veristand and verify that it will work and deploy that. But as I said, that's just one example. There are several other tools that can import these FMIs, making it possible to create a complete workflow. But also sometimes you would like to, you have some work you have done in some other tool and you want to import it to SystemModeler, and then you can do that with the same FMI functionality but using the import functionality of it. So tools that can export FMIs are, amongst others, listed some here, including ANSYS SCADE, IBM Rational Rhapsody, Control Build, and so on. So by developing something in one of these tools, you can then use that in SystemModeler. So why would that make sense? Let's illustrate that with an example from our fierce competitor, Simulink. So Simulink is used especially within the control systems, within control system design. So there's a lot of controllers designed in Simulink. And in this case, what we'll have is a drivetrain model that has been developed in SystemModeler, and we want to use a controller developed in Simulink. So let me run that in Simulation Center. As that has been exported, the FMI from Simulink, I really I don't have Simulink on my computer. But here is the model, and you see there in the middle there's something missing. That's the FMU that I haven't imported yet. But if I click into this here, we see the SystemModeler model of the drivetrain with a transmission and driver and so on. This is something I've shown in previous presentations, so I won't go in previous years. I won't go into details how the model itself works. That's not really the topic of this presentation. But what I will do is I will import this FMU, import FMU from Simulink, and cruise control like that. And now, there you go. So here I have imported that, and actually we can see here that I had predefined the controller here in the system, and then it will pop up in my model. So now I have this Simulink controller controlling my driveline, and I have some input signal, a very simple reference signal there that I can use. And I can then simulate that from within SystemModeler without any need of Simulink or any other software. It's just, it knows everything that was from the Simulink model and can run it here. So this, by the way, what's going on here is compiling the simulation code, the thing I mentioned first. So that executable that was compiled now is the one that you can use for deploying and creating your own simulators. Now I can plot, let me close this so we have a little bit more, can see a little bit better. I can plot the reference speed, but I can also plot the measured speed of the car. And in this case, I can see, for instance, if I zoom in somewhere, that we lose some speed every now and then, and I guess most of you can guess what's going on when that happens. Anyone? Why is that happening? Gear shift, yeah. And if it would have been Andreas driving, the gear shift would have been much smoother. He's a very good driver, so it would work much better. Okay, so that shows the reason why you would like to import something to SystemModeler. You might have parts and model like a controller from Simulink that you want to reuse. You don't want to redo that, but you want to use the full potential of system modeling for the plant. And then you can develop that plant to this car in this case and add the controller from Simulink. For this, I won't show an example, but you can also, to the Modelica code, call external functions. So in the Modelica code, you can reference to DLLs and to C files. And basically, that means to anything that can be wrapped into a C file. So any code you have that can be wrapped into a C file, you can reference to that in the Modelica model and compile it with the entire model. So if you happen to have some kind of algorithm developed for, what do I know, like a lookup table that you're using for something, then you can plug that into the Modelica model and run it just as if it was Modelica. You can also communicate with executable itself. So once you're running, you can connect to it through a TCPIP protocol, so anything that can speak TCPIP. You can query the simulation for different things, like query it for results, but you can also set things like start, stop time, pause, restart, change inputs. So you might have, for instance, connect some kind of device, let's say a gamepad to your computer, and have that to control your simulation. So that you can use the TCP/IP protocol for. So let's see here. One example here, which you could use for that, is you could develop your own custom applications in any kind of software. In this case, somebody has generated some software there on the left-hand side where he uses that to kind of, which displays the results, but also by pushing in different places, it changes parameter values, and it goes to the model, runs that, and feeds information back. Okay, so now we're getting there. So model plug was added, I think, about 4 months ago, something like that, or perhaps more. But the idea with model plug is to be able to connect to Arduinos or any board that uses the Firmata protocol. So to easily connect to an Arduino board, how many here knows what an Arduino is? Almost everyone. How many have used an Arduino? Quite a lot. Okay. So typically when you use the Arduino, you have to, well, you do some wiring and stuff, and you create your experiment, and then you have to code the communication for it. The idea with this is by using the model plug library, you will be able to connect that with drag and drop. So let me just show the web page first for the model plug library. So basically, with the model plug library, you will be able to create different examples, and I will show these examples soon. You would create a robot arm or an inverted pendulum and use that. You can download it, and it's free. So this screen resolution is not the best, but you can see it's a free download. So it's just download it, and then you can use it for whatever purposes you would like to have it. So let's start with, before we go live, I think that I wait for that to last, so the thing you might remember is that I failed the last thing I did. So this is one example of something you can set up. We have built a robot arm and some control panel with some knobs. To control that robot arm, you could connect the control panel directly to the robot. But what will happen then is that the signals from the control panel are pretty rough, which means that the robot will move very what's it, kind of opposite to smooth. I'm losing words here. So it will kind of jump from one place to another. So you want to filter the signals in some way. And then, so this is the simplest example of what you could be doing with the SystemModeler, the model plug models. So you have this system here, the board, and then just a couple of filters for the signals, and then the robot arm. And what I will do is I will just show a video of how it works. We'll see the actual library and example live soon. I just wanted to give you some examples of things you can do. So here you can see that we have the robot, we have the plate with knobs. This is connected to the computer, and what we see here is simulation center, and we are plotting, I think it's the position in XYZ direction for some point of the robot. And you can plot whatever you would like to, just as you would do in any SystemModeler simulation. So if I run this, you will see that the plots are there, and you can see the robot is moving. It's not that easy to see, but it's actually adding, you see here, it's adding information as we go on the plot. Another example, and I kind of like this, is that one was a lot hardware and very little software. In this case, we're going the other way around. We're doing this model here, where we have an accelerometer, and we connect that to a model of an inverted pendulum. And then we try to use the accelerometer to give the pendulum disturbances and see how well it can control itself. So let's look at that. By the way, on the way here, the most classical, of course, is to do the blinking LED and have it type hello world, as you saw on the Raspberry Pi presentation earlier on. That's, of course, something you could do here, too. Here. So here we have the accelerometer, and we can see the SystemModeler model where the inverted pendulum is moving in order to balance your pendulum. And the accelerometer is not that good, so it's actually a little bit hard to give it exactly the signals you want, but you can implement it better. And then of course, what you can do here is to develop, to have an exercise for the students or for yourself. How do I do to develop the controller in order to actually balance this as good as possible? Or you could do some other experiment using that as a reference. Where do I want to move my pendulum, rather than hitting with it? Or you might have another one to tell it the reference position or whatever you want to add to make the system more complex. So let's look at the balancing a ball on this one here. So before we actually use the hardware, we'll take a look at the model. Here's the 3D version modeled in SystemModeler. So of course that was not what I was aiming to do. Of course we have modeled this in SystemModeler also completely, so without any hardware to begin with. But anyways, here is the model. We have, if I click into this, we can see that this is the Arduino board, and the Arduino board is basically communicating. We have which pin or servo are we connecting to with pin 2, a port, and this is the card itself, the Arduino board, and we are telling it which port it should connect to. So if we go up to upper level here, we see that the only thing we have done is drag and drop together the different pins and the different boards we're using, and we're setting up basically which port is it I'm supposed to talk to. In this case, I hope it's COM9 still. It might change sometimes, and then I have to check which one it has changed to. So you just set up, the only kind of program you need to do is to write down which port to communicate with, nothing else. Okay, so let's try to run this. Hopefully this will, I'll have to set it up to run real time, I guess, for infinity, and synchronize with real time, like that. Now hopefully, when I run this, oh, sorry. We'll have something happening there. Yeah. Okay, so now we see it actually doing something. So basically in the model, what we have set a reference point for where we want this ball. And then the controller is inside my computer, is a SystemModeler simulation. And then when I move the ball, of course, it tries to get it back. And it's actually pretty good at doing that. So that was interesting. It worked the first time. So now you might want to experiment with stuff. What happens if I try to do something more like that? Kind of managed to do that. But you might want to start looking at things in the model itself. So let us try here to design another controller quickly. And that just by changing parameters. So I go into the parameters for the controller here. And go to, let's say, well, let's say that we start with the easiest one. If we change the P part, the proportional part, what would we expect? Anyone from controls? What would we expect if we change the proportional part? Well, it's actually pretty bad, because the proportional part is the most important. So it doesn't really achieve what we wanted to achieve. So let's stop that again, switch back. Then we can change something else, like the derivative part, and I have no idea what would happen here. Let's increase that. Will probably not work that well, but who knows? Yeah, it's kind of not as good as the original one, but it's hopefully making its work at some point in time. So yeah, okay, there you go. So it was a bad controller. But in this way, you can experiment and test different controllers. And of course, to design the controller, you can use the control functionality in Mathematica, and that's what has been done when they designed the other controller. So I'm pretty sure that I will not be able to, by random, find a better controller than the one that is right now. Do I dare to put the ball here? No. Okay. Stop it. There you go. Okay, so you get the idea here. It's quite easy, and all of these things are low cost. So it's a simple Arduino board where they have done some kind of wiring, put a few capacitors and things on it, connected that, and then connect this hardware with a servo, which you can control. You control the servo signal from the Arduino board, and that will control the angle. In this here, we have a couple of sensors, which are measuring basically light sensors, so they are measuring the distance of the ball, and that is what you need to set up, and then you have connected to SystemModeler using the model plug library, and you have your experiment going on immediately. So it's kind of up to your fantasy and the kid in yourself to come up with good experiments that will teach you stuff, and then you can I can change the reference position and so on. There's tons of things I could do. So that is what I was going to show with the Arduino, and I have like 2 minutes left, I think, and for that I will say coming soon. So coming soon is a similar library, but in a sense I would say it's the professional model plug. It's basically for process industry mostly. So there's the standard OPC, the process industry, which is used for data communication. So in the very same way as the model plug is used by drag and drop, in this case you will have drag and drop components for OPC, and instead of connecting to this guy here, you will perhaps connect to a brewery, or I don't know what you would like to connect to. I would be interested in controlling that at least, or produce or have, let's say, ethanol production, or have your printer, etc. You can printing press. You can any kind of process industry would have the OPC applied to the OPC standard, and then you can do similar things like controlling the actual plant from SystemModeler using the OPC protocol. Or you can just use it to monitor, so you read signals from it, and then you might have models that can predict what is going to happen in the future. You might have, let's say you have 1,000 sensors out there, and then you want to understand what will happen in different scenarios, which scenarios could happen based on the information you're receiving. Then you can simulate that and predict different alternatives depending on pulling in perhaps data from Wolfram Alpha or from weather data to see a projection on where we're heading, how we should control the system, and so on. But in principle, works the very same way as this one, just on a larger scale and slightly more expensive. So with that, I'll thank you very much, and I'll hope you have a good end of this conference. Thank you.